the change of basis formula from lecture 63A is a little bit complicated. So in this lecture we're going to work out an extended example of applying the change of basis formula in a simple situation. I've copied the change of basis formula on the right of the slide there. What we're going to consider is a linear map T from r squared to r squared, defined by T of x, y is equal to minus 16x plus 6y minus 45x plus 17y. We're going to consider two different bases of r squared. The first, e, will be the standard basis, written as e1 and e2. So e1 is the column vector 1, 0, and e2 is the column vector 0, 1. And our other basis, f, will be 2, 5 and 1, 3. And I'm going to call the first of those vectors f1 and the second of those vectors f2. What we're going to do is to apply the change of basis formula to work out the matrix of T with respect to initial basis f and final basis f in terms of the matrix of T with respect to initial and final bases E and the other things which appear in the change of basis formula. So let's think carefully about what's going on. We have T is going from r squared to r squared. And we will have two bases of the domain of this, E and F, and two bases of the codomain, again, E and F. So if we apply the change of basis formula, what it would tell us is that the matrix of T with respect to initial and final bases f will be equal to the matrix of the identity on r squared with respect to initial basis E and final basis f times the matrix of T with respect to initial and final bases E times the matrix of the identity with respect to initial basis f and final basis E. What we're going to do is compute the matrix on the left-hand side of that equality by working out the three matrices on the right-hand side of the equality and multiplying them together. So we'll begin with the easiest one, which is the matrix of T with respect to initial basis E and final basis E. You will remember how we work these out. What we have to do is to work out T of E1 as a linear combination of E1 and E2. That will tell us which numbers go in the first column of the matrix of T with respect to E. So T of E1 is T of 1, 0, which, when we work that out, is minus 16 minus 45. And T of E2, that's T of 0, 1. Again, you can substitute x equals 0 and y equals 1. When you do that, you get 6, 17. So that first calculation told me the first column and the second told me the second column of this matrix. And so what we get is that matrix of T with respect to initial and final bases E is the matrix minus 16 minus 45, 6, 17. We discussed the matrix of the identity in a previous lecture, and we observed that when your final basis is the standard basis, it's actually very easy to work out the matrix of the identity in that case. So that suggests that the easy one of the two matrices of the identity matrix here should be the one where the final basis was E. The reason that that is easy is because what you have to do to figure out the first column is work out the identity of F1 as a linear combination of E1 and E2. But of course the identity applied to F1 is just F1, which is 2, 5, and that is 2E1 plus 5E2. And similarly, the identity of F2, well, that's just F2 again, which is the vector 1, 3, so that's 1E1 plus 3E2. So the identity has matrix with respect to initial basis F and final basis E 2, 5, 1, 3. In other words, its columns are just F1 and F2. So now what we'd like to work out is the remaining matrix on the right-hand side of the equation star. So that is the matrix of the identity with respect to initial basis E and final basis F. So let's move on to a new slide to work this out. What we're looking for is the identity with respect to initial basis E and final basis F. Well, of course, we could do this using the definition. What we would need to do is to work out the identity applied to E1 as a linear combination of F1 and F2. So these stars are supposed to represent some number which you need to work out, and then those two numbers that you find would go in the first column of the matrix of the identity with respect to initial basis E and final basis F. I mean, this is not particularly difficult here. You just have to solve some simultaneous equations. You have two linear equations in two variables which you need to solve to find what this is. But there's an easier way. The easier way is to observe a useful property of matrices of linear maps. So let's consider what happens when I multiply the matrix of the identity with respect to initial basis E and final basis F, and the matrix of the identity with respect to initial basis F and final basis E. The theorem on the matrix of a composition of linear maps tells you that this is the matrix of the identity composed with the identity with respect to initial basis F and final basis F. That was a couple of videos ago, so you should review it if you've forgotten it. So of course the identity composed with the identity is just the identity. And we saw, again, a couple of lectures ago, that the matrix of the identity map with respect to the same initial and final bases is the identity matrix. So here we just get the 2 by 2 identity. And what that tells us is that the matrix EF and FE, so matrix of the identity with respect to initial basis E and final basis F, and the matrix of the identity with respect to initial basis F and final basis E, are inverses of one another. Therefore, this matrix that we wanted is equal to the inverse of the matrix that we just worked out. So what's that? We worked out that the matrix of the identity with respect to initial basis F and final basis E was 2, 5, 1, 3. And so its inverse, using the usual formula for the inverse of a 2 by 2 matrix, is 1 over 2 times 3 minus 1 times 5, which is just 1. And then we have 3 minus 1 minus 5, 2. This is a useful trick which saves you from having to solve a bunch of simultaneous linear equations. So it's very useful to remember this. We now know all three of the matrices on the right-hand side of our change of basis formula, so we're ready to do this. I get that the matrix of T with respect to initial and final bases F is the matrix of the identity with respect to initial basis E and final basis F, times the matrix of T with respect to initial and final basis E, which turned out to be minus 16, 6, minus 45, 7, times the matrix of the identity with respect to initial basis F and final basis E, which was 2, 1, 5, 3. Okay, you can do these matrix multiplications. When you do this, you should find that the result is minus 1, 0, 0, 2. So how could I check that I have the right answer here? I mean, I've just got some matrix here. It's not really obvious whether or not this is correct. So how could we check this? Well, here's a good way to check. What this says is it tells us how to express T of F1 as a linear combination of F1 and F2. That's what the first column of this matrix means. So the first column here is saying that T of F1 should be equal to minus 1 times F1 plus 0 times F2. In other words, T of F1 should be minus F1. And similarly, looking at the second column, what that tells us is that T of F2 should be 0 times F1 plus 2 times F2. So let's see whether one of those is true. We'll work out T of F1. So that is T of 2, 5, which is minus 16 times 2 plus 6 times 5. In the top place, minus 45 times 2 plus 17 times 5. If you work that out, you can see that you really do get minus 2 minus 5, which is minus F1. So it looks like we've managed to do this without making a mistake. And similarly, if you check T of F2, you'll find that you really do get 2 times F2. So our calculations here are correct. So as one final observation here, you might wonder, why would I bother doing this? So what is the point of writing a linear transformation or finding its matrix with respect to one basis and then finding its matrix with respect to a different basis? This example shows why that might be useful. Because if you just know the matrix of T with respect to the standard basis, so that was this matrix in the middle here, that doesn't seem to tell you anything useful about T. It doesn't give you any clue as to what T is doing. It just looks like 4 fairly random numbers, and you wouldn't really have a good understanding of the linear transformation T just by looking at those 4 numbers. On the other hand, the matrix of T with respect to initial and final basis F, which we computed to be this diagonal matrix minus 1, 0, 0, 2, is much more revealing because it tells you in an intuitive way what T is doing. It tells you that if you have a matrix, which you write in terms of a component in the direction F1 and a component in the direction F2, so I mean as a multiple of F1 plus a multiple of F2, then what T does is simply to multiply the component in the direction of F1 by minus 1 and multiply the component in the direction of F2 by 2. So that has a nice simple geometric description. Vectors in the direction of F1 get multiplied by minus 1, so they get their direction swapped. And vectors in the direction of F2 get doubled in length by T. So you now have a easily to understand geometric interpretation of what T does, which would not be at all obvious by looking at its matrix with respect to the standard basis. So just as multiple bases can give you different ways to look at a given vector space, and you'll remember our image processing example to illustrate that, looking at the matrix of a linear map with respect to different bases can give you an insight or a different way to look at what that linear map actually does.